So, as Shelley said, my name is Michael Hutchins. I'm a graduate student in the Earth and Space Sciences Department at the University of Washington. And similar to Ian, I plan on graduating fairly soon. So today I'm going to be talking about the problem of finding lightning. And first, so why it's important. So imagine we're all on an airplane together. I'm sitting there flying an airplane. I assume this is how you fly an airplane. And all of a sudden, boom, hit by lightning. First off, we'd be a little bit shocked at the situation. Nobody? Okay. But then, fortunately, we're in a modern aircraft. A modern aircraft can actually withstand lightning without being, crashed or destroyed. Probably would want to land and get an airplane. But it would have been good to know that there was lightning nearby before we started flying our airplane. And that's one reason why it's important to know where lightning is occurring around the world. It's also useful for, say, weather prediction. So if we know where lightning is, we kind of can get an idea of where weather is around the world. Current weather. Also, say, if you want to know if your church is about to be hit in Green Lake, it's good to know if there's lightning nearby. And there's also some good scientific reasons to help understand climate, thunderstorms, and the effects of lightning around the world, say, into space. So to find lightning, I want to talk about the ingredients that go into making it. So first off, how to make a thunderstorm. Now, we don't get many thunderstorms here in Seattle, so it's a good review for everyone who hasn't really experienced them. But the two main ingredients for a thunderstorm are warmth, say from the sun, so late summer, mid-afternoon, and humidity. So a lot of moisture in there. It's getting muggy, it's getting hot. And what happens is the land and the ground start to heat up. So you have all this, the sun's beating down, it's heating up, it's warming up, and all this hot air then starts to rise up. And as the hot air rises up, the moisture in the air, you mentioned it's humid earlier, starts to precipitate and turns into a cloud. And at first that's pretty good. It's a hot day out, it's sunny, maybe the cloud gives us a little bit of shade. But that cloud continues to form as more hot air rises up into it. And what eventually happens is as the hot air rises, it has to go somewhere. So the hot air rises up, and then it cools down as it rises and comes back down to the ground. And this process continues. It's called convection, similar to how water boils on your stove. And the thunderstorm continues to grow. And it starts to rain. Maybe the sky starts getting dark. There's a big thundercloud over us. And that movement of air inside the cloud allows for the cloud to become electrified and allows it to charge up. And as it charges up, we start getting lightning. And there's really two main types of lightning. There's lightning that happens within a cloud, or between different clouds, and that's the majority of lightning. And there's lightning that we normally think of and see, which is from the cloud down to ground. So that's kind of what goes into creating lightning. So then how are we going to find where it's happening? Well, one thing that happens in thunderstorms and with lightning is they produce thunder. And one way in the past that was used to find where lightning is around the world is something called thunder days, which I think is a fantastic term that we should bring back. And what a thunder day is, it's a day that has thunder. Not a particularly complex name or consideration. And how we used to get the information about what thunder days is we had people around the world, volunteers, maybe operating a weather station, and you just listen throughout the day. And eventually, you sit down and you hear thunder. You sit at your desk and your little notebook counting thunder days, and you hear thunder, and you check it off. There was thunder that day. And you send this report off to some central weather agency, and they compile all of the data together, and they look at it, and they're able to produce maps such as this one, which are both difficult to read and not particularly helpful. So maybe after a year or two, after you record your thunder days, they bring it together. And most people, when you think about lightning, you think of it just like a big static shock. So a static shock, if you haven't accidentally shocked yourself ever, is say you're driving on a hot day in the middle of summer and you get out of your car, you touch the frame, and you get a small static shock. Or if you're walking on a carpet and you touch a doorknob and you get a small static shock. So most people think of lightning as a static shock, but just instead of you and a doorknob, just a thunderstorm and the ground. But we have technology like high-speed cameras that lets us look a little better and a little closer at what's happening when lightning strikes the ground. So this is a video of lightning. It's going to start in the upper left corner. I assume it is playing. Uh-oh, maybe, oh, there we go, now it's playing. And as it starts, it branches the ground. So you have all these branching fingers, exploring, trying to find ground. But when you're up at the top, it kind of goes in a random direction until one part eventually touches ground. And what you see when you see lightning in the horizon in the distance is not this branching. What you see is the bright flash. So knowing that, we see it's clearly a very complex electrical process. It's not a simple static shock. It's more like 100 to 1,000 of small static shocks that eventually part of it find ground. So if we want to find out and find lightning and locate it, we know, okay, it's an electrical process. It produces a bunch of light. Maybe that can help us. So for that, we need to take a small detour through our friend, the electromagnetic spectrum, and go through what type of light is there, and what does lightning produce, and how could this help us locate where it is. So we're going to start on the far right of it with gamma rays. So gamma rays are really short wavelength light. When I say short, probably really hard to imagine how small they are, and usually you don't encounter these on your day-to-day life unless you're, say, a gamma knife technician at a hospital. And so in this, you use gamma rays, as you put like say you're the one going in surgery, you put a head brace on, and it shines gamma rays at a bunch of different directions in your head to, say, burn out cancer cells in your head without having to cut you open. So they're pretty useful for medical reasons, but generally you don't really encounter them on a day-to-day basis. Going down, so that's really short wavelength. Going down a longer wavelength, we have X-rays. X-rays almost everyone is familiar with. You break a bone, you want to know how it's broken. You go into the dentist to see if you have any cavities in the health of your teeth. So again, pretty useful, but even if lightning produced these, maybe it wouldn't help too much in finding out where they occur. So then we go to ultraviolet light. Most people are familiar, or if you're from Seattle, you've heard of ultraviolet light. It's in sunlight. It's a thing that helps give you a tan or maybe a sunburn, or if you're unfortunate, skin cancer. And we tend to protect against it with, say, sunblock. Now, going even longer wavelengths, the perennial favorite type of light, visible light. Everyone's usually a fan of visible light. Lets you see, lets you look at wonderful slides at presentations such as this one. And these are kind of forms of light people are pretty comfortable thinking as light. Once they're getting longer, you don't really think of it as light. For example, infrared light. Maybe everyone here, I'm sure, has experiencing it right now. But you've definitely experienced infrared light if you've ever gone camping. So if you're camping, it's a long day, you're huddled around your campfire to warm up from the heat. And you notice is that the part of you illuminated by the campfire light is the part getting warm. So if someone steps between you and the fire, you suddenly get really cold because you're now in the shadow of the infrared light from the fire. So you push them aside to get the heat back. So it's not the hot air from the fire heating you up, unless you're standing in it. It's the infrared light coming with fire and illuminating you. And similar for other types of light, so microwave light. So they can use, say, heat up food in your microwave. So say you're cooking a Hot Pocket, it'll heat up half of it to be really hot and half of it will remain cold. Or if you use cell phones, I assume most people do, cell phones use microwaves to communicate. So now we're at longer wavelengths to the point where we can talk about how long they are. So microwaves for cell phones are about maybe an inch in length. So if you have your cell phone from 10 years ago, say you've never upgraded, the antenna on it is about an inch in length because that's how big microwaves are. And we can go to longer wavelengths. So we go to radio. So your car antenna for your radio is about 3 feet long. It lets you listen to, say, KUOW as you're driving up I-5. And we get even longer, and to transmit in radio waves, we have these really tall radio towers on top of, say, Capitol Hill that broadcast AM and FM radio through the whole area. Now, if we think about it, say X-rays, they don't go very far. Cell phones go a little bit farther. You can, from here you can reach a cell tower even though you can't see it in this room. And then radio waves go even farther than all of them together. So to help us locate and find out lightning, we want to know what type of light does lightning produce. And so now it's time for a quiz. I hope everyone brought pen, pencil, maybe a blue book or a Scantron to fill out the answers. You guys didn't bring that? Okay. Well, maybe we can shout out answers later. So what type of light does lightning produce? Well, there's X-rays and gamma rays at the high end. Okay. Radio waves, seems plausible. Visible light, very likely. All the above, so maybe produce all this light. Or maybe like, Michael, I've never seen lightning. It just doesn't exist. So if everyone had a chance, think about the answer, and if everyone just yell out what type of light you think it produces.
E.
I heard one E. We kick that person out. Lightning produces all of these. So lightning and lightning processes produce everything from radio waves all the way through to gamma rays. And knowing this and the different types of light available, we see radio waves are probably our best bet. You see radio waves at really long distances away, and if you think back, lightning is similar in size to a radio tower. It's just a long, tall object, essentially in the sky, just producing radio waves across the entire world. So to take advantages, at the University of Washington developed the Worldwide Lightning Location Network, which, as the name may imply, locates lightning around the world. For brevity, I'm going to abbreviate this to talk as the WWLLN. And you may think, that's no better. There's just as many syllables there. There's all those W's and L's. Fortunately, a previous graduate student of my advisor noticed WWLN originated in New Zealand. And New Zealand is full of sheep. So you think about that for a second. Think about it like, aha, we'll call it woolen. A lot easier to say. So how does it work? So the way the network works is kind of a reverse game of Marco Polo, where we have lightning producing all these radio waves, and we listen to where it's happening. So to demonstrate this, I want everyone to close your eyes. Don't worry, nothing bad's going to happen. And now I realize we have these speakers might not work. Point to where you hear my voice coming from. So everyone just go and point. Good enough. So keep where you're pointing and open your eyes. If you follow where you're pointing, and you draw, say, a line, you know that I'm somewhere on this line, or the speaker is somewhere on that line. But you don't know if I'm standing really close to you talking quietly, or far away talking loudly. But if you look at someone else on the other side of the audience, and see where they're pointing, and you draw the two invisible lines on the ground, you can kind of pinpoint where I was. And you get more people to do this, you can get a better idea of where I was standing on the stage when I was talking. So that's what we do. Instead of sound and pointing, we use radio waves. And we have 70 stations spread out around the world. So we have one in Seattle, one out in Forks, Alaska, all different continents. We have 6 in Antarctica, which I think is pretty neat. Though, despite my best efforts, I've never been able to go there and fix them. I told friends to go kick them over when they're down there so I could get sent. And so how this works is, say there's lightning down here in the South Pacific, and it's producing a blast of radio waves around the world, and it's picked up by 5 different stations. And based on what those 5 different stations report, we can say, aha, that lightning occurred down in the South Pacific. And we're able to find lightning like this to within a few kilometers, so a couple miles, we can locate its position, and to a fraction of a second. And what's more, we can do this in real time. So instead of producing a map like this, that takes several years to compile and doesn't tell us much about what's happening today, we can produce much higher resolution, use color, and get a better idea of where lightning is happening around the world. So here's just showing where lightning is happening with more lightning in red and less lightning in blue. So if you remember back to when I said what you need to make a thunderstorm, you need humid air and a lot of heat. So places that are hot and humid get a lot more lightning and thunderstorms than places that are not. So say the South has a lot more lightning than up here in Seattle, which if you're from there, you'll say, of course. But you ask, well, what about places like, equatorial regions that you've never been to, and you want to know what type of lightning is happening there? So with this network, we're able to find lightning located around the world, and we actually do provide the information to airlines for airline safety. We can provide it for weather services to say where lightning is occurring. You can help forecast, because imagine there's a hurricane coming in off the Atlantic Ocean, and once it gets close to land, we have a bunch of radars to know where it is, but where you have places with not much weather infrastructure, it's useful to know where, say, lightning is to help predict where that thunderstorm is moving, to predict where it's going to go. And there's also other benefits for, say, space science research and other climate research. So that is how we find lightning. But before I finish, I want to show you one more thing that I hope works. There's a website everyone can go to, woolen.net/new/map, that is a map of the current lightning activity around the world as of 30 minutes ago. So get this running, and I'll also have this on as I finish. Full-sized. And if the internet's working, we can see this is where lightning is happening around the world as of 30 minutes ago, April 9th. And so this to prove that I'm not just making things up, but we actually do locate lightning in real time. Thank you, and I'll be glad to answer any questions.
So what's the difference between lightning and what we refer to as heat lightning, where you just see it simmering on the horizon?
So I'm not 100% sure, but I believe heat lightning happens when there's lightning and no rain. And what happens is there is rain falling from a thunderstorm in that situation. It just is so hot it evaporates before it hits the ground. So you could have a cloud in the sky in a distance and get lightning, but not have any rain nearby.
Just as a reminder, we'd love to capture this all on audio recording, so if you can come up to the mic, that would be great. Thank you.
Hi. Hello?
Hi.
Right, so just a sort of method you're describing is sort of a form of triangulation, right? So in terms of placing the different, what do you call those towers?
Stations.
Stations. What's sort of like the optimal sort of range for a station? Like where do you know when and where to place when?
So the placement of the stations is really dependent on two main factors. One, someone to host a station. Since this is a university project, we can't pay people to run these for us. So usually there's a university or institute at these locations. And then also someone like me actually building the stations. They're kind of the two main components. And in an ideal world, they'd be evenly spaced around the world. But there are places that just don't have the necessary infrastructure to. It's like the middle of the Sahara Desert doesn't have broadband and consistent internet, and consistent energy or power to run the stations. But generally, I want them maybe 2,000, 3,000 miles apart.
But just related on that, do you have a picture of a station? Like how big is the station? What does it look like?
I don't have a picture on hand, but I can just describe it to you. It's about a 2-meter antenna. So you have an antenna about this big, that's just simple wires. Go into a small preamplifier box, so you have like an amplifier for like a speaker system, and that runs into just a small computer sitting on a desk, plugged into the internet. It's not complex in any way, and that's why I'm able to build them.
So are you able to log the intensity of the strike?
Yes, as of about, it froze, that's embarrassing. Pretend that didn't freeze. So as of about 4 or 5 years ago, yeah, we have been able to get a measure of the strength of the lightning by essentially looking at the total power of the signal at each station as it receives it, and then using a Navy transmission model to work backwards to say how strong the lightning had to be to see that strength at the station. Oh, it's running again. Oh, no.
The cloud's on.
We have a question in the audience. Sorry about this. So now you see the lightning is happening in clouds. So it's definitely working. And again, this is a website everyone here can go to. Don't recommend doing it on an iPhone. The iPhone will probably crash.
So if you go back to your map of worldwide coverage.
Let me see if I can get this. That one?
Down there in South America, you have a band, sort of a whole little activity. Is that?
That area?
Yes. Is that real, or is that an artifact of station placement, or?
If I'd have to guess, it's probably the predominant wind pattern is going from west to east. And so most of the rain will rain out on the Andes, and there'll be a rain shadow in that area. I do not believe that is an artifact of our network.
Yeah, above it you have the intertropic convergence zone where it will be convective activity most all the year, but there'll be a seasonal, so that'd be interesting to see if it's...
Yeah, it could be definitely a seasonal signal because this is all year and lightning does have a seasonality to it.
Isn't that area basically the Atacama Desert? So it's shielded by the Andes, basically, so there's no
Yeah,
any moisture come through.
I'd say it's the shielding from the Andes
Yes.
is probably the predominant factor. Go back to showing this.